Welcome, curious minds, to another deep dive. Today we're plunging into a topic that, for many, can feel pretty daunting, almost like trying to read Moby Dick for the first time, interpreting nuclear magnetic resonance or NMR spectra.
Yeah, those squiggly lines.
Exactly. All those peaks, so much information. It's like, where do you even begin? But don't let that intimidate you. Our mission today is really to make sense of it all,
Hmm.
turning what might seem like overwhelming data into, well, a fascinating puzzle.
That's absolutely right. A lot of textbooks just say, work lots of problems and promise you'll, get the hang of it.
Right, which isn't always that helpful.
No. It often leaves learners feeling a bit lost, like they're just sort of waving a flashlight around in the dark, hoping for a lucky guess.
Yeah.
So this deep dive, we're aiming to give you a systematic strategy. Think clue gathering, like a detective on a case.
A method to the madness. We'll walk you through a proven way to figure out molecular structures using NMR, breaking down all that complex data into manageable steps. Think of it as maybe a shortcut to getting informed, giving you those aha moments without the usual info overload. Okay, let's unpack this.
Let's do it.
So, every good detective starts by sizing up the scene. For NMR, that means gathering our first crucial pieces of evidence. What kind of clues are we actually looking for? How do we kick off the investigation?
Okay, so our approach is very systematic. It has to be, really. And it's adaptable, too.
Adaptable how?
Well, you might get different kinds of NMR problems, right? Some give you just the molecular formula and the proton NMR, the 1H spectrum.
Okay.
Others might throw in IR, maybe a mass spec, or even a carbon-13 NMR.
Right, more clues.
Exactly. Our method lets you use whatever clues you're given. We generally start by figuring out the degrees of unsaturation, the DOU, from the molecular formula.
Okay, step one.
Then, if you have it, look at the IR spectrum. That can tell you about major functional groups.
Teach a shortcut.
Then we use the integration from the proton NMR to work out molecular fragments, pieces of the puzzle. Once we have those fragments, we start piecing them together, making sure it all fits with the chemical shift, the peak splitting, the details. And finally, super important, we double-check our proposed structure against all the evidence. Make sure it all lines up.
Sounds like a solid investigative roadmap. All right, let's dig into these clues.
First up, clue 1. Determine the degrees of unsaturation, or DOU, from the molecular formula.
If you have the formula, that is.
Right, if you have it, this is your crucial first step. There's a formula for it you can look up, pretty simple. Number of carbons x2 plus 2, number of hydrogens 2.
Okay.
But what it tells us is the powerful part. It reveals how many double bonds or triple bonds or rings must be in the compound. Each double bond or ring counts as 1 degree of unsaturation. A triple bond counts as 2.
Gotcha. And what about other atoms?
Good point. Quick conversions for halogens. Fluorine, chlorine, bromine, iodine. You add 1 hydrogen to your count for each one before you use the formula. For nitrogen, you subtract 1 hydrogen for each nitrogen.
Right.
Oxygen or sulfur. You can just ignore them for this calculation. They don't affect the count.
So if that DOU number comes out as, say, 0.
0 means no double bonds, no triple bonds, no rings. The molecule's saturated, fully loaded with hydrogens, basically.
And what if it's higher? You mentioned benzene rings.
Exactly. That's where it gets really useful. A DOU of 4 or more. Well, that's a very strong hint. You might be looking at a benzene ring.
Because a benzene ring has 1 ring and 3 double bonds, 4 degrees total.
Precisely. So this single number, the DOU, it gives you a quick high-level snapshot, narrows down the possibilities right away.
Okay, great first step. Once we've got the DOU maybe hinted at a ring or double bonds, what's next? You mentioned IR.
Yeah, clue 2. Look at the IR spectrum, if it's provided, to determine major functional groups.
How helpful is IR compared to, say, just relying on the NMR?
It can be very helpful. Sometimes the IR signal for a specific functional group is just, well, unmistakable. A big, strong peak. Carbonyls are a classic example. That strong stretch around 1,700 inverse centimeters.
Right.
NMR can usually confirm these later, but IR can sometimes just scream out carbonyl or alcohol or carboxylic acid right at the beginning. Aldehydes, benzene rings. These often give clear IR signals, too. It helps you confirm or rule out big chunks of structure early on.
Makes sense. Get the big pieces in place.
Yeah.
All right, so DOU, then IR. Now let's dive into the 1H NMR itself. You mentioned integration curves.
Yes, clue 3. Determine the peak ratios by measuring the heights of the integration curves. This is where we start counting hydrogens.
Okay, how does that work? I see those sort of S-shaped lines over the peaks.
Exactly. That's the integration curve. The height of that step, like how high it jumps vertically, is directly related to the area under the peak it covers.
And the area tells us?
The area tells you the relative number of hydrogens that peak represents. It's like a head count for each unique type of proton in the molecule.
So how do you measure it? Just get a ruler out?
You literally could, yes. Or often the software does it for you and gives you a number. You measure the height difference for each integration step.
Okay.
Then, to get the relative ratios, you divide each of those height values by the smallest height value you measured.
Ah, so you get ratios like 1 to 2 or 1 to 3, something like that?
Exactly. Now, integrations aren't always perfect whole numbers in real spectra. You might get something like 1.0 to 1.5.
What then?
If they're really close, like 1.8 or 1.98, you can usually just round. But if it's like 1.0 to 1.5, you multiply both parts of the ratio by the smallest whole number that makes them both integers.
So 1.0 to 1.5, multiply by 2.
Right, that gives you a 2 to 3 ratio.
Okay, so that gives us the relative ratio. How do we get the absolute number of hydrogens for each peak?
Good question. You sum up the numbers in your relative ratio. Let's say it adds up to 5, like a 2.3 ratio.
Okay.
Then you look at your molecular formula. How many hydrogens does it actually have? Let's say the formula says 10 hydrogens.
Right. Our ratio sum, 5, doesn't match the total 10.
Exactly. So you need to multiply your entire relative ratio by whatever factor makes it match. In this case, 10 divided by 5 is 2.
So multiply the 2.3 ratio by 2 gives 4.6.
Precisely. So one peak represents 4 hydrogens, the other represents 6 hydrogens, and 4 plus 6 equals 10, matching the formula.
That's critical, isn't it? The final numbers have to add up perfectly.
Absolutely critical. The sum of all the hydrogens you assign from the integrations must exactly match the number of hydrogens in the molecular formula. If it doesn't, something's wrong. Maybe your ratio calculation, maybe even the assumed formula. It's a vital check.
So, thinking like our census taker, integration tells us how many people live in this house, which is incredibly valuable. Okay, we've got the counts. What's clue 4?
Clue 4 is break the NMR peaks into fragments. Using the integration from clue 3, now we turn those numbers into actual pieces of the molecule.
Okay, how do we do that?
Well, you start assigning each peak with its known number of hydrogens to a likely fragment. A peak integrating for 1H often means a CH group, like on a double bond, or next to several other groups. 2H usually means a CH2, a methylene group. 3H is almost always a CH3, a methyl group.
Makes sense. What about larger numbers?
Larger integrations often point to specific common groups. 6H, showing up as a doublet, for instance, frequently suggests an isopropyl group, 2 equivalent CH3 groups.
Ah, the CH-CH3-2 unit.
Exactly. And 9H, especially if it's a singlet, is very often a tertiary butyl group, a T-butyl. That's CCH33.
Okay, so you list out these potential fragments based on the integration number.
Yes, write them down. CH3, CH2, maybe a COH from the IR, whatever pieces you've identified.
And then?
Then, another crucial check. Add up all the atoms in the fragments you've listed. Add up all the carbons, all the hydrogens, all the oxygens, etc.
And compare that to the molecular formula.
Exactly. They must match perfectly. This helps ensure you haven't missed any atoms, like maybe a carbon with no hydrogens attached, or forgotten the oxygen from a carbonyl you saw in the IR.
Good self-correction step. Now, you mentioned something about symmetry being a potential pitfall here.
Ah, yes, that's an important point. Sometimes a molecule has symmetry. This can mean that chemically identical protons show up in the same peak.
So a 2H peak might not be a CH2.
It might not be, though it usually is.
Yeah.
For example, think about diethyl ether. CH3, CH2, He2, CH3. The two CH2 groups are identical due to symmetry. They'd show up as one peak integrating for 4H.
Okay.
Or, a slightly trickier case mentioned in some texts is dimethylylene. It has two CH groups that are actually identical by symmetry. They show up as a single peak integrating for 2H. So it looks like a CH2, but it's actually two separate symmetric CH groups.
So you have to keep symmetry in mind, especially if the simple fragments aren't quite adding up or fitting together later.
Exactly. Always consider those possibilities, especially if the puzzle pieces just aren't clicking into place. Look for potential symmetry in the molecule.
All right, so we've got our DOU, functional groups from IR, and now a list of fragments with the right atom counts. We're holding the puzzle pieces. What's clue 5?
Clue 5. Combine the fragments in a way that fits with the NMR peak splitting, chemical shift, and degrees of unsaturation. This is the grand assembly.
Putting it all together, how do we approach this? Do we just start sticking fragments together randomly?
Hopefully not randomly. You start by brainstorming, thinking about all the possible ways your fragments could logically connect.
Okay.
Then you use the other NMR data, primarily peak splitting, but also chemical shift, to systematically eliminate the incorrect structures.
How does splitting help eliminate structures?
Okay, so peak splitting, or coupling, tells you about the neighbors of a given proton. Remember the n+1 rule?
Right, and neighbors means the peak splits into n+1 lines.
Exactly. A proton with no neighbors is a singlet. One neighbor, a doublet. Two neighbors, a triplet. Three, a quartet, and so on. Sometimes it's more complex, a multiplet.
So if you propose a structure where, say, a CH2 group has 3 neighbors,
Then its signal must be a quartet, 3
Right.
plus 1, 4. If the actual spectrum shows that 2H signal as a triplet instead, then your proposed structure is wrong.
okay. The splitting pattern has to match the predicted neighbors.
Precisely. Symmetry also plays a role here. If your proposed structure is highly symmetric, it might predict fewer peaks than you actually see in the spectrum, or vice versa. Chemical shift helps too, are the protons where you'd expect them based on nearby groups.
Got it. You also mentioned some common patterns to look out for.
Yes, these can save you a lot of time.
Yeah.
Recognizing common groups by their combined integration and splitting patterns.
Like the ethyl group.
That's a classic one. A quartet peak integrating for 2H, coupled with a triplet peak integrating for 3H. That pattern almost always screams ethyl group, and that's just CH2CH3.
Yeah, that's a good one. Any others?
Yeah, an isopropyl group, and that's CH3 That usually shows up as a multiplet, often a septet, 6 plus 1, 7, for the single CH proton, and a doublet integrating for 6H for the two equivalent methyl groups.
1H multiplet and a 6H doublet.
Got it. And the t-butyl group, NACH3. Because the methyl groups are attached to a carbon with no hydrogens, they have no neighbors to split with. So you see a sharp singlet integrating for 9H.
9H singlet equals T-butyl. Okay. Recognizing those patterns must speed things up considerably.
It really does. Turns chunks of the puzzle into pre-assembled pieces.
All right, so we've assembled a candidate structure that seems to fit the fragments, the splitting, the shift, the DOU. Are we done?
Almost. One crucial final step. Clue 6. Recheck your structure with the NMR and the IR spectrum. Verification time.
So this isn't just looking back at the clues, it's something more specific.
Yes. For this clue, you take your proposed final structure and you forget about the original spectrum for a moment. You look only at your drawing.
Okay.
And you predict, from scratch, what its 1H NMR spectrum should look like. Go through it proton by proton or group by group. How many unique proton types are there? What should each one integrate for? What should its chemical shift approximately be? What should its splitting pattern be?
You're building the theoretical spectrum for your answer.
Exactly. You predict the entire thing. Then you compare your prediction in detail to the actual spectrum you were given.
And they need to match perfectly.
Perfectly. Pay close attention to chemical shift here. Are the protons near electronegative atoms like oxygen or halogens shifted downfield, high ppm like they should be? Are aromatic protons in the right region? Are protons next to carbonyls around 2.5?
Okay. And if it doesn't match?
If it doesn't match, don't panic.
Yeah.
First, double-check how you connected your fragments. Is there another way to assemble them that you missed? Often, there is.
Right.
If rearranging the fragments doesn't work, then you might need to revisit clue 4. Did you assign the fragments correctly? Could there be symmetry involved that you didn't account for?
Yeah.
Maybe that 6H doublet wasn't an isopropyl group after all in this specific case?
Go back a step and reevaluate the pieces.
Precisely. It's an iterative process sometimes.
Okay, that whole process, those 6 clues, seem really systematic. Theory is one thing, but maybe we could run through an example.
Absolutely. Application is key. Let's try one from the sources.
Okay.
First case. We're given the molecular formula C8H8O2 and its 1H NMR spectrum. No IR this time.
C8H8O2. Okay, clue 1.
Clue 1, DOU. Let's calculate. 8 carbons, X2, plus 2 is 18, minus 8 hydrogens gives 10. Divide by 2.
5. 5 degrees of unsaturation.
Right. And 5 degrees, especially with 8 carbons. What does that strongly suggest?
4 or more. Likely a benzene ring.
Very likely.
Yeah.
That has a 4 degrees right there. So there's one more degree of unsaturation somewhere else, maybe another double bond or another ring.
Okay. Clue 2 is IR, but we don't have one. So clue 3, integration.
Right. We look at the NMR peaks. Let's say we measure the integration steps, find the ratios. Suppose going from left to right, downfield to upfield, the relative ratio comes out as 1 to 2 to 2 to 3.
1.2.2.3. Let's check the sum. 1 plus 2 plus 2 plus 3 equals 8.
And the formula is C8H8O2, so it has 8 hydrogens.
They match. So the relative ratio is the absolute ratio.
Perfect. So we have peaks representing 1H, 2H, 2H, and 3H. Now, clue 4, fragments. But wait, before assigning fragments, let's look closely at the chemical shifts here, as clue 2 would normally involve looking for obvious functional groups, even within the NMR.
Okay, what do we see in the spectrum?
Well, way downfield. Around 13 ppm, there's a broad peak. Integrates for 1H. What does 13 scream?
Very deshielded. Carboxylic acid proton?
Bingo. That broad singlet 1213 is characteristic of a COH group. That accounts for our 1H peak and also uses up both oxygens and the extra degree of unsaturation, the CO double bond.
Nice. So we found the deduce OH. What else?
Then between 7 and 8 ppm, we see two sets of peaks. This is the classic aromatic region.
Confirming the benzene ring we suspected from the DOU.
Exactly. Now, how many hydrogens do these peaks represent? Our ratios were 1.2, 0.2, 0.3, and we've used the 1H for the acid. So the aromatic peaks must be the 2H and 2H ones. Total of 4H in the aromatic region.
Okay, 4H on a benzene ring means it must be disubstituted, right? 6 positions total, minus 2 for substituents leaves 4 hydrogens.
Perfect. And here's a key observation. We see two distinct peaks, or sets of peaks, maybe doublets, in that region, integrating for 2H each, not 4 separate 1H peaks. What does that symmetry imply?
If there were 4 different aromatic protons, we'd expect 4 signals. 2 signals for 4 protons suggests symmetry, like maybe the 2 substituents are parallel to each other?
Exactly. A paired disubstituted benzene ring often shows this pattern due to symmetry making pairs of protons equivalent. Ortho and meta would usually give more complex patterns with 4 distinct signals, so we've refined disubstituted benzene to paired disubstituted benzene.
Wow. Okay, so our fragments so far are TIC-COH and a paired disubstituted benzene ring, which accounts for C6H4. What's left?
We use the 1H, 2H, and 2H integrations. The only one left is the 3H integration. What fragment is 3H?
A methyl group, an SCH3.
Right. So our fragments are DEC-COH, a paired disubstituted benzene ring, and XCH3. Let's check the atoms. COOH is CHO2. The ring is C6H4. The methyl is CH3. Total, C1 plus 6 plus 1, H1 plus 4 plus 3, O2. It matches the formula perfectly.
Great. Now clue 5, combined fragments. We have NaCOH, DACCH3, and the parabenzene ring needs 2 things attached.
Well, there's really only one way to put those 3 pieces together, isn't there? Attach the gamma COH to one side of the para ring and the NaCH3 to the other side.
Which gives us p-toluic acid.
Precisely.
Okay, final check. Clue 6. Confirm. Predict the spectrum for p-toluic acid.
All right. The methyl group, NaCH3, is attached to the ring. It has no proton neighbors. Should be a singlet for 3H. Where would it be? Attached to a ring. Maybe around depot 32.5 ppm.
Okay. The aromatic protons, we said para-substituted, 4H total, showing us 2 signals due to symmetry. Probably doublets coupling to each other across the ring in the 7-8 region.
Yeah, maybe 2 doublets, each integrating for 2H, and the carboxylic acid proton.
The EGO-H proton, a singlet, 1H way downfield, 1213.
Okay, now we compare that prediction to the actual spectrum we were given, and let's assume it matches perfectly. The 3H singlet is at 8.2.3, the 2 aromatic doublets, 4H total, are between 7 and 8, and the 1H singlet is at 13.
It all fits. Case closed. P-toluic acid it is.
Nicely done. Want to try another, maybe with IR this time?
Yeah, let's do it. Example 2, C5H10O, and we have both 1H NMR and IR spectra.
Okay, C5H10O. Clue 1, DOU. 5C by 2 plus 2 plus 2 minus 10H equals 2. Divide by 2.
1. 1 degree of unsaturation, so 1 double bond or 1 ring.
Correct. Clue 2, functional groups from IR and MR. Let's look at the IR spectrum first this time. Anything stand out?
Let's say the IR shows a really intense peak right around 1710 centimar.
1710, classic carbonyl stretch region.
Right. Could be an aldehyde or a ketone. Is there an aldehyde CH stretch around 2700, 2800?
Let's say no, nothing there. And the formula only has 1 oxygen.
Okay, so no aldehyde CH, only 1 oxygen. It must be a ketone, not an aldehyde, not an ester, not an acid.
Good deduction. It's a ketone. And that CO double bond accounts for our 1 degree of unsaturation. So no rings, no other double bonds.
Excellent. Ketone identified. Now, clue 3, NMR peak ratios. Let's look at the proton NMR integrations. Suppose they come out as 1.0, 1.0, 1.0, 1.55.
Okay, not whole numbers. What do we do?
Multiply by 2 gives 2.3, 0.2.3.
Right. Now check the sum. 2 plus 3 plus 2 plus 3 equals
10. 10 hydrogen.
And the formula is C5H10O.
It matches, so the absolute integrations are 2H, 3H, 2H, and 3H.
Perfect. Clue 4, fragments. What fragments do these integrations suggest?
So H is probably CH2, 3H is probably CH3, so we have 2 CH2 groups and 2 CH3 groups.
That seems most likely. So fragments are CH2, CH3, another CH2, another CH3. And don't forget our ketone carbonyl CO from the IR.
Right, let's check the atoms. Carbonyl is CNO, 2 CH2s are C2H4, 2 CH3s are C2H6, total C1 plus 2 plus 2, H4 plus 6, O1, C5H10O, it matches.
Great, all atoms accounted for. Now clue 5, combined fragments. We have a ketone group, 2 CH2s and 2 CH3s. How can we put these together?
Well, a ketone has the CO in the middle of a chain, typically, so it needs alkyl groups attached to both sides of the carbonyl carbon. We have two CH2s and two CH3s to use.
Okay, can we make a symmetric ketone, like put a CH2, CH3, and ethyl group on both sides?
Ethyl group is C2H5. Two of those would be C4H10. Add the carbonyl carbon, CH10.
C5H10, oh, that fits the formula. The structure would be CH3, CH2, CO, CH2, CH3, diethyl ketone. Okay, that's one possibility. What's another way? Could it be asymmetric? Maybe an ethyl group on one side and... Wait, we need to use a CH2 and a CH3 for ethyl. What's left?
We use one CH2 and one CH3 for the first ethyl. We have another CH2 and another CH3 left. Oh, wait, that doesn't work. Let me rethink. Our fragments are CH2, CH3, CH2, CH3.
Maybe think of it as needing to form two alkyl groups to attach to the CO. We have 4 carbons total in the fragments, 2 CH2, 2 CH3.
Okay. We can make a methyl group, CH3, and a propyl group, CH2, 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 CH3. Let's say methyl uses 1 CH3, propyl uses 2 CH2s and 1 CH3. That uses 1 CH3, 2 CH2s, 1 CH3. Perfect, it uses all our fragments.
Right, so the asymmetric possibility is diethyl ketone, symmetric, and 2-pentanone, asymmetric. How do we decide?
Look at the NMR spectrum again. How many distinct peaks did we see? Our integrations were 2H, 3H, 2H, 3H. That's 4 separate signals.
4 signals. Okay, now think about the structures. Diethyl ketone, CH3, CH2, CH2, it's symmetric, right?
Absolutely. There's a plane of symmetry through the carbonyl. So the two CH3 groups are identical, and the two CH2 groups are identical. That means it should only have 2 signals in the NMR, one for the CH3s, one for the CH2s.
But our actual spectrum has 4 signals.
So diethyl ketone is ruled out. It must be the asymmetric one. 2-pentanone, CH3, CH2, 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 CH3.
Excellent deduction. The number of signals immediately eliminated the symmetric option. This happens quite often.
Okay, so our proposed structure is 2-pentanone, clue 6, confirm, predicted spectrum.
Right, 2-pentanone. CH3A, CO, CH2B, CH2C, CH3D. Let's label them A, B, C, D from left to right.
4 distinct types of protons. That matches the 4 signals we saw. Good start.
Okay, proton A, the methyl group next to the carbonyl. It has no neighbors on the carbonyl carbon, so it should be a singlet integration.
3H, chemical shift, next to CO, so deshielded, maybe 2.1, 2.2.
Sounds right. Okay, proton B, the CH2 next to the carbonyl. How many neighbors does it have?
It's next to CH2C, so it has 2 neighbors.
So it should be A.
Triplet, integration 2H, shift, also next to the carbonyl, maybe even slightly more downfield than the methyl. Say 2.4, 2.5.
Good. Now proton C, the middle CH2. How many neighbors?
It's next to CH2B on one side, 2H and CH3D on the other, 3H. Total of 2 plus 3 equals 5 neighbors.
5 neighbors.
Yeah.
So N+1 rule predicts a sextet. Integration 2H. Chemical shift. It's further from the carbonyl, so more upfield than B. Maybe 1.5, 1.7. Okay. And finally, proton D, the methyl group at the end of chain. Neighbors.
Just the CH2C group next door. 2 neighbors.
So it should be a triplet. Integration 3H. Shift. It's furthest from the carbonyl, most shielded. Maybe around D.9.
Okay, let's recap the prediction. A, 3H singlet at D2.1, B, 2H triplet at D2.5, C, 2H sextet or multiplet at 1.5, D, 3H triplet at D.9.
Now we compare that prediction to the actual spectrum. And let's assume it matches perfectly. The shifts, the integrations, the splitting patterns all line up.
Then 2-pentanone is confirmed, case closed. That systematic approach really works.
It does. It turns it from guesswork into logical deduction.
Even with a clear strategy like that, though, I imagine it's easy to make mistakes, especially when you're starting out. Do the sources mention common pitfalls?
They do. 3 big ones are highlighted. Mistake, #1. Trying to determine a structure from chemical shift alone.
Just looking at the ppm value and trying to say, oh, that must be a proton next to X.
Exactly. And it's almost always a mistake, except for maybe a few really characteristic shifts like aldehydes or carboxylic acids.
Why is it usually wrong?
Because the chemical shift regions overlap a lot. You might see a peak at, say, 2.5 ppm. That proton could be next to a carbonyl, or it could be next to a benzene ring, or next to a double bond or triple bond, or even just a couple of other electronegative groups.
So the shift alone isn't specific enough most of the time?
Not usually, no. You can't reliably identify most fragments just by their shift. It's much better to understand the general ideas behind chemical shift, like electronegativity, pulling electrons away makes protons deshielded and shift them downfield, or how pi systems in double bonds and rings create local magnetic fields that also cause shifts. Understand the concepts gives you flexibility.
Rather than trying to memorize a huge table of precise values that overlap anyway?
Exactly. Use shift as supporting evidence and for the final check, but don't rely on it for initial fragment identification.
Okay, good advice. What's mistake #2?
Mistake #2, starting with coupling.
Ah, okay. I can see why that's tempting. The splitting patterns seem to tell you immediately what's next to what.
It seems like it, but remember our census taker analogy. Integration tells you how many people live in this house. It gives you the size of the fragment.
Right.
Coupling tells you how many people live next door. It tells you about the neighbors. It's much harder to figure out the pieces of the molecule if you start by focusing only on the neighbors.
You need to know what the pieces are before you worry too much about how they connect.
Precisely. Plus, coupling can get complicated. You can have long-range coupling. Sometimes chiral centers mess up simple patterns. Doublets might not be perfectly symmetrical.
And sometimes you just get that messy multiplet or haystack.
Exactly. A jumble of peaks that's hard to interpret precisely, especially early on. Coupling is most powerful in Clue 5 when you're trying to figure out the connectivity of the fragments you've already identified using integration.
Start with integration for fragments. Use coupling to connect them. Got it. What's the third common mistake?
Mistake #3. Confusing integration with coupling.
Ah, mixing up the two concepts.
Yes, and it's critical not to do this. They tell you completely different things. Integration is about the area under the peak, which tells you the relative number of protons represented by that peak.
The head count.
The head count. Coupling, or splitting, is about the number of lines the peak is split into, which tells you via the n+1 rule about the number of neighbors those protons have.
How many live next door?
Right. They are independent. You can have a peak that's a complex multiplet, lots of neighbors, but only integrates for one H.
Like the CH in an isopropyl group.
Perfect example. Or you can have a peak that's a sharp singlet, no neighbors, but integrates for 9H.
The t-butyl group.
Exactly. So, never assume the height or complexity of the splitting relates directly to the number of protons. Integration gives you the number of protons. Splitting gives you the number of neighbors. Don't mix them up.
That's a really clear distinction. Okay, avoid relying only on shift. Start with integration, not coupling, and don't confuse integration with coupling. Solid advice. Wow, what an incredibly thorough deep dive into solving NMR puzzles. It really does transform what can seem like just noise into a logical step-by-step process.
It does. And once you get comfortable with this systematic approach, you might find, as I do, that solving spectroscopy problems can actually be, well, pretty fun.
Like solving a code.
Exactly. They're puzzles. Just puzzles where the rules are dictated by the laws of physics and chemistry.
And that's the beauty of it, isn't it? Taking something complex, breaking it down into manageable clues, identifying the pieces, and then methodically figuring out how they fit back together. It's a way of thinking, a skill that honestly extends far beyond organic chemistry labs.
Very true.
So maybe a final thought for you, our listener, to mull over. Think about other areas in your life. Are there any seemingly overwhelming data sets, maybe complex situations or projects that could benefit from this kind of clue-gathering approach?
Yeah.
Breaking it down, looking for patterns, piecing it together systematically. Could you transform chaos into clarity elsewhere, too?
Interesting question.
Something to think about. Thank you so much for joining us for this deep dive into NMR problem solving.
My pleasure.
Until next time, keep exploring, keep questioning, and stay curious.